CUDA is high level. You can do a lot of different things. I'll show you a code snippet of a difference between CUDA and OpenCL. I don't want to really take sides in this. They're kind of different. They have different target audiences. You can do kind of different things. Like in a way, CUDA is, if you write everything up front, you're basically, it's a compile time thing. You're writing all the kernels that you're going to want to run, and it's going to be locked down at compile time. With OpenCL, you can actually change your kernels at runtime and be creating kernels on the fly based on what you think you need to do. And that's actually really interesting for Apple because a lot of their APIs, the core whatever, core animation, core compute, core data, whatever, they build a lot of things on the fly based on what any given application is going to do because the application is actually programming these APIs. So they're starting to want to build things on top of OpenCL so that they can do compute-intensive things but built on the fly. So that's really interesting for them. And kind of underneath the hood of all of this stuff for us is this common PTX ISA. And I know you guys have talked in your class about instruction set architectures. This is kind of a semi-machine independent ISA, meaning that as future GPUs evolve, we will continue to support this ISA. We might support extensions to it and so forth like that, but every GPU we make for a very long time is going to continue to support this ISA. Even if the underlying machine language is somewhat different. And yeah, this is basically talking about the tool chain if you're using CUDA. That basically you use a front end that splits it off into a real CPU version and a GPU version, and then later on combines it back together into a unified program. And we have spent a long time on tool chains for not just building it, but debugging it. I mean, when things go wrong on the GPU, it used to be that you were completely in the dark. You had no idea what went wrong and no way of finding out. Now there are actually really good tools, and we just released something recently. It was called Nexus, and it's now, it's called something else, but it's basically integrated with Visual Studio. So if you're using the Microsoft toolchain, it lets you use that to debug what's going on the GPU and even like somewhat step through it. Which is new and kind of cool. So, CUDA, OpenCL. This is why it's not immediately obvious to everyone that they want to switch to be able to do everything on the fly. Because to do everything on the fly, you're making a lot of API calls to change the way things are set up and state and manage your textures and all kinds of things in a much more explicit way. You can do the exact same things with these for the most part. But you're going to need a lot more wrapper code with OpenCL because it's just a lower level way of talking with things. And I presume the same is true of direct compute, but I work on Apple stuff, so I'm a little removed from that. And just, basically, this is getting a lot more common. Yeah, it's great for us, but it's also great for everybody who needs to do anything parallel. Because, Intel, AMD, us, we're all on it, and it's doing really well. I guess the last thing to say is just that it's less and less important now that you're working on a GPU. What's really more important now is that you've got a processor that's really good at serial and a processor that's really good at parallel. You don't really care that it's a graphics processing unit. You care that you've got serial and parallel and you need to know what each one is good at and how to use them. And that's kind of the way things are moving. So kind of the future, where are things going? Right now, everything's driven by the CPU. The CPU basically says, hey, go do this. And when you're done with that, hey, go do this. And when you're done with that, hey, go do this. And the GPU can do a lot of operations on that data that, as it's told by the CPU. But it's basically data that comes from the CPU or that it's modified on. As time goes by, though, it gets more interesting to have, say, producer-consumer, persistent threads that are running on the GPU that are processing things as they come. There's a lot of different kinds of workloads where maybe the GPU is going to, it's important that the GPU can create work for itself. I know we're thinking about that. We talk about that a lot. I know our competitors think about that. They talk about it a lot. Again, that's just a little bit more general purpose. So kind of the future path is imagine what's more general purpose, and that's kind of where things are likely to go. Also, you know, I talked about the debugging development environment and in Microsoft's platform. Well, not everybody uses Microsoft. You know, it doesn't matter how cool the technology is. If the tools to support it aren't any good, people won't use it. You know, if you can develop this really great algorithm, but you can't figure out what's wrong with it, you'll give up on it and move away. So there's as much effort it goes into the hardware, equally, maybe more, goes into the software that supports that hardware. The driver to make sure that it goes fast, that we can correct for some common mistakes that programmers make, that the tool chain is there. You know, that's all really important. And so, you know, we talked about the trade-off between parallelism and serialism. What's important, you know, like, what is parallelism good for? And basically, there's a lot of things that are obviously good parallel. And these are, you know, graphics, yeah, of course. I mean, that's where this all came from. The one I'm actually really keen on is computer vision. You know, you guys have all probably heard about the DARPA challenges and, you know, robotic cars that are driving themselves. That's a hugely parallel task. I have no doubt that 20, 30 years from now, I'm going to have a car that can drive itself. And everything it's doing is going to be essentially looking at the road through some version of a camera. And that's a hugely compute-intensive task. Now, maybe 30 years from now, NVIDIA will be bankrupt and gone, but it's going to be highly parallel systems that are doing that kind of work. And scientific computation, all these things, like, this is just going to be more and more ubiquitous, and parallelism is, now that it's available, it's going to continue to grow. Also, you know, I'm sure you guys all know about it, but serial things also, we're getting close, you know, we're always getting closer and closer to that limit where serialism falls apart, where you just can't process any faster serially, and so at that point you have to scale out. And so it becomes important to find a way to parallelize what you do. Even if it's not something like graphics or computer vision that's obviously parallelizable, you still, if you need to go faster than you are now, you're going to have to find a way to parallelize it if you can. So, again, from an NVIDIA perspective, but you know, the interesting problems that haven't been solved yet tend to seem to be throughput problems. How can you process through the largest amount of the data in the shortest possible time? I've been saying this all along, but basically, we're becoming the general purpose throughput processor. We're getting more general, but we're going to continue to be parallel. The CPU is getting more parallel, but it's probably going to continue to be largely serial in nature. Just because well, yeah, that's just basically the way things are. It probably will continue to be. This is definitely the NVIDIA company line. I think it's probably true, but put it through your own filter, which is that we think CPUs have reached where they can go. I mean, they've got some legs left. They will continue to go. But for most processes, the CPU is good enough. You don't need that much faster of a core than you've got. You really, though, still need computation, and parallelizing out, that's kind of the natural place to go. So, I mean, obviously, we think that's why we're in a good spot. I don't want to evangelize too much on that, but this is kind of the whole point of this class, is thinking about how to use this right. I mean, not NVIDIA, how to use NVIDIA right, but you know, how to think about parallelism right, how to get the most out of what you're doing for what you do. Okay, so I've hopefully left some time for questions, and if you guys have questions about how the driver works, I can definitely tell you the layout of the hardware, like how things will actually flow through the hardware and not this high-level description. I can tell you whatever you're interested in, fire.
So is Fermi going to be, you know, mass consumption, like a consumer level thing, or is it going to be mostly just a server station?
No, it's definitely mass consumer. Yeah, there will be the Quadros, you know, the $2,000 cars, and yes, there will be the Tesla stuff that is, you know, the 60